So phasor relationship for circuit elements. Now we put it apply in what we so call the electric circuits. So the voltage current relationship for a resistor in the time domain. This is the time domain. We have applied plus minus V. This is our resistor. We have I. So V equals to IR. Oh, so easy. And then what about we put in a frequency domain? The phasor domain is called as a frequency domain. So we can highlight it become V, volts V. Volts V means vector. Vector means it has a direction. Then we box the I, then we have R. So we have V equals to IR. So we begin with the resistor. If the current through a resistor R is I equals to Im cos omega t plus phi. Im is the peak of the I. Then this is AC. The voltage across is given by the Ohm's law, V equals to IR. So I have my I like this, right? So I copy R, then I copy Im here, I copy cos omega t plus phi here. Then I change into phasor form. So when I change into phasor form, it is a vector. So my V will be volts. And then R will be copy, Im will be copy, cos become angle, then I copy the psi into this. But the phasor representation of the current is like this. So from here, we know that I is like this. I copy Im. The cos will be angle. This is my phi. So which is the same as Im angle phi. Then I can put this, both I become here. So we will have V equals to IR, where V and I are both together as a vector. We also can represent the phasor diagram for the resistor, where my real is here, imaginary is here. So if my I, first of all, to put into the phasor diagram, we must know where is I. So my I, for example, is IN psi. So I put I like this. Then this is my psi. If I times with R, I have my V. For example, my I, if let's say if a 10 ampere, my resistor maybe is 10 ohm. So our voltage will be 100. Then it will become longer than I, but the same direction. Okay? For inductor. So the voltage current relationship for inductor in the time domain is like this. If you still remember in the chapter 2 we talked about inductor. So V equals to L di dt. So plus minus V, this is I, this is L. We also can convert into frequency domain. How can we get the V equals to J omega Li? We'll go through here. So we have a vector of a V, we have a vector of the I, this is L, then plus minus V equals to J omega L times I. So for the inductor, same as well, we need to assume what is the value of the I. So I equals to Im cos omega t plus theta. Then the voltage across the inductor will be V equals to L di dt. So we substitute the I into here. Then we differentiate the I. Then we will have negative omega Lim sine omega t plus phi. How can we get this one? Very easy. We differentiate with time. So L I copy. When I differentiate the cos, I have a negative value. Negative omega. So I have a negative omega and sine. When I differentiate, so I copy the Im. And then I copy plus phi. So this is how we get this one. Recall from equation 9.10, negative sine A equals to this. We can rewrite the voltage like this. Because this is a sine wave. So we want to convert into cos so that we can put into a phasor form. So we transform to the phasor. So, and then our Vm will become omega Lim. Okay, sorry. Maybe I should look through this one. We know that negative sine A is a cos A plus 90. So negative sine A, which is a cos A plus 90. So I throw out negative, I change the sign to cos. I throw out negative, I change the sign to cos. And then my A is omega t plus phi. Omega t plus phi. Phi or psi? Phi. and then I copy plus 90 here. So this is how we get the V equals to omega Lim cos omega t plus phi plus 90. And then we want to change into a phasor form. Now, several phasor form we can change. Either we change to omega Lim exponential j phi plus 90 degree. Or we can change to omega Lim exponential j phi times exponential j 90. Or the easiest way, omega Lim with angle phi plus 90 degree. But we know that my I is actually Im phi angle of phi. So I can substitute this one. And from equation 9.19 is the top. Exponential j 90 degree is actually j. So we can put extract this 90 degree become as a j. So just now this is no j, it becomes j. Omega Lim, omega Li copy. Im angle of a phi is this one. So I just put in as a I. So showing that the voltage has a magnitude of omega Lim. This one omega Lim, this is voltage. And the phase of phi plus 90 degree. The voltage and the current are 90 degree out of phase. Specifically, the current lags the voltage by 90 degree. So how we can draw in a phasor diagram? I should say that this is how we get our voltage equals to j omega Li. And then how can we put in the phasor diagram is very easy. Draw the real and imaginary part. Determine where is I first. So my I is actually Im with the angle of a phi. So I with the angle of a phi. Just simply put there in the positive way. And I know that the voltage is 90 degree more than Im. So I just draw a 90 degree. And I put 90 degree this one. And then this is my voltage. So every time when we want to draw the phasor diagram, two axis, where is I? Then we'll see the equation. So we can see that V is leading I, or we call I is lagging V. How to see that? When I stand here, two of them rotate. Okay, so V will come first, and then I will come later. So in chapter 2, we talk about how the equation of the capacitor, so which is I equals to C dV dt. So VIC, we also can write in the frequency domain, where V equals to I equals to j omega CV. And then this is how we derive. So for the capacitor C, assume the voltage crosses are just the previous two cases, the resistor and inductor, we assume I first. Now we need to assume V because we are dealing with the dV dt. So we assume V equals to Vm cos omega t plus phi. Same, we start with the cos first. So that then we differentiate with time t. And then do the same calculation. We will have I equals to j omega CV. Or V equals to I divided by j omega c. And then we draw in phasor diagram. We found that I is leading with V. So when we want to draw the phasor diagram, please remember one is a real part, one is imaginary part. Then we need to draw the so-called the reference first. V equals to Vm cos omega t plus theta is actually the reference first. Okay. Then we know that the I is a 90 degree from the V, so we just draw like this. So I is the leading of V, because when I stand here, when it's rotate, we see the I first, and then V will be later. As a summary here, so element of R and L is some sort of the same. R is a V equals to IR, frequency will be V equals to IR, RI, this is the frequency domain. L is equals to V equals to, for element inductor, V equals to L di dt. Then we can write in the frequency domain as a V equals to j omega L I. Then for the capacitor element, time domain I equals to C dV dt. Frequency domain V equals to I over j omega C. So let's have a look on the example. The voltage V equals to 12 cos 60t plus 40 degree is applied to a 0.1 Henry inductor. Find the steady state current through the inductor. So this is an inductor. What formula we need to use? V equals to J omega Li, where our omega is 60, right? And V is equals to, so I change this one to polar form. I copy 12, cos is angle 40 degrees like this. Then I substitute, I move the V here. Sorry, I should say like that. I rearrange the equation, become I equals to V over J omega L, and then V I just copy here, and then J omega is a 60, L is my 0.1 Henry. Then I found that I found 2 angle of 45 degree in ampere. I change into time domain. So I copy 2, I change the angle to become cos. I know that my omega t is I copy minus 40. I copy my omega t, which is 60 t. Okay, next we talk about impedance. The impedance of a circuit is the ratio of the phasor voltage V to the phasor current I measured in the ohms. In chapter 2, we talk about resistance value, capacitance value, inductance value. When we deal, that one is in AC circuit. When we deal with sorry, that one is DC circuit, in direct current. When we deal with the AC circuit, it involves frequency. So when we involve frequency, we need to change all so-called the passive element into impedance. For example, V equals to Ri. So my R will be V over I. Then V equals to J omega Li. So I can make it V over I become J omega L. V equals to I over J omega C. I make it V over I become 1 over J omega C. So my Z is actually equals to V over I. Then V equals to Iz. Okay, so this is all my impedance. We can do it like this. As a summary, the resistance, the impedance will be Z equals to R. Admittance is 1 over Z actually, so become 1 over R. Impedance of the L is equals to J omega L. My admittance is become 1 over J omega L. My capacitance is of the impedance 1 over J omega C. Then my admittance is equals to 1 over Z, which is 1 J omega C. So we can write our impedance R equals to Z equals to R plus minus JX. And then also can turn into polar form, where Z equals to magnitude of the Z with the angle of theta. Or we can, as a summary, we can do like this: Z equals to R plus minus JX equals to like this. And then where angle of the Z is actually square of R plus X squared and square root. And then the angle will be theta equals to arctangent plus minus X over R. If we still remember the complex number, Z equals to X plus JY. If let's say we want to find the R, which is this value, we need to use X squared plus Y squared and then square root, which is the same. It is the same things. Just for information, for inductor, it will short circuit at DC, and then it will open circuit at high frequency. Or the capacitor, it will open circuit at DC and then short circuit at high frequency. Let's have a look on the inductor L. So if the frequency is very high, frequency is very high means omega is very high, then impedance will be very high. When impedance is very high, it will open circuit. So in DC circuit, the frequency almost 0, so it will be short. Then for capacitor, let's see the impedance value. If very high frequency, very low frequency, let's have a look on the very high frequency. If it is very high frequency, so 1 over very high frequency, 1 over very high frequency, which is 1 over 100,000, for example. So the impedance will be almost zero. When it is almost zero, it means nothing. The current just directly can pass through. So it becomes short circuit. On the other hand, in a DC state, it becomes open circuit. Huh? So let's have a look on the simple circuit. For example, this is a circuit connected to the resistor and capacitor with the source 10 cos 4t. So now we need to find the VT and IT in the circuit. I want to find the VT here. I also want to find the IT here. So what I need to do is I need to convert the voltage source to polar form first. So Vs become, I copy 10, cos become angle, 40 I don't want, and then I know that it starts from 0. Then the impedance will be, add up together, 5 plus 1 over j omega c. So my omega is come from here, 4. So it is 4. My c is 0.1 farad. So I use calculator, I find this one. Then I find my current, which is I use Vs divided by total load. So Vs is actually 10 angle of 0 degree. My load is this one. So I convert into, actually I just use calculator lah, and I can find this value. After that, I want to find the V here, right? So I use V equals to Iz. Use I times this Z. So I know that my I is like this, my Z is j omega c. So I use the I, which is here, this value, and then divide by j times omega. Omega is 4, c is 0.1. Then I use a calculator. We found this one. So I found V value. Next, I need to find I value. I value found it already. So I need to convert both of them, the I and the V, into time domain. So how can I do that? I copy I, 1.789, I copy 1.79, angle become cos, 26.57, then omega t. Omega t is this one, 40, so I plus 40. Same for the VT, I copy 4.47, angle become my cos, I copy negative 63.43, and then I copy my omega t. So this is my IT and VT. Okay, impedance combination, it is the same as in the previous chapter 2. When we have impedance in a series, so our Z equivalent can be V over I, which is Z1 plus Z2 plus Z3 until plus Zn. We also can use voltage division. If I want to find the voltage here, I use Z1 divided by Z1 plus Z2 times V. Remember, you will still remember the chapter 2. Voltage division will be V1 divided by total voltage, total impedance, then times the total voltage. Or if let's say I want to find V2, I use Z2 divided by total impedance times total voltage. In the same manner, if let's say we want to find, if the impedance are connected in parallel, so same as the previously we talked about in current Kirchhoff law, we want to find the Z equivalent. Actually, is a 1 over Z equivalent equals to 1 over Z1 plus 1 over Z2 plus 1 over Zn. Okay? Or, for example, for this case, if let's say, this is a current division. If let's say I want to find, it is same as in a DC circuit. If let's say I want to find I1, it's very easy. I use Z1 divided by Z1 total impedance times I. Or, if I say I want to find I2, I use Z2 divided by total impedance times I. Let's have a look on the example. So find the input impedance of the circuit in a figure 9.23. Assume that the circuit operates at omega equals to 50 radian per second. Z1, I have a 2 millifarad. Z2, I have a 3 ohm and a 10 millifarad. Z3, I have a 0.2 Henry and 8 ohm. So the first thing is we need to change R into impedance. So Z1, where is Z1? It's 2 millifarad. I use 1 over J omega C. Omega is given 50 radian. C is a 2 millifarad. I have negative J10. Jack 2, 3 plus Jack, or 3 plus 1 over J omega C. Omega is 50, C is a 10 millifarad. I have this one. Same as well, Jack 3 is 8 plus J omega L. It is in series. So, I have this one. So the impedance here is I need to combine this one and this one. These two are parallel. So as an easy way, Jack 1 plus Jack 2 parallel with Jack 3. So it becomes Jack 1. So when parallel means I use this one times this one divide by total of this one. Then I found that this one. So instantaneous and average power. Power is the most important quantity in the electrical utility, electronic, and a communication system because such system involves transmission of power from one point to another. Also, every industrial and household electrical devices, every fan, motor, lamp, pressing iron, TV, personal computer, has a power rating that indicates how much power the equipment requires. Exceeding the power rating can do permanent damage to an appliances. The most common form of electric power is a 50 to 60 Hz AC power lah. The choice of the AC over DC allows high voltage power transmission from the power generating plant to the consumer. We begin from defining and delivering instantaneous power and average power. So the instantaneous power is in a watt, is the power at any instant of time. So we see when we write P, we must have a T. And then P, we know that P equals to VI. And then when we want to find the P at that time, we need to use the T, the V at the time, and the I at the time, times together. So sinusoidal source and a passive linear circuit. So for example, we have a Vt equals to Vm cos omega t plus theta V. We have a It equals to Im cos omega t plus theta I. Then we use these two together, times together. Then we have this thing. And then we apply this formula. Then we will find out this one. So from this equation, this shows that the instantaneous power has two parts. The first part is a constant part or time dependent part, independent part. Then it is a value depend on the phase difference between the voltage and the current. This is the phase difference theta V minus theta I. And then the second part is the sinusoidal function whose frequency is a 2 omega, which is twice the angular frequency of the voltage and the current. So from this equation, we can know that actually we also observe that Pt is a positive for some part of the cycle and negative for the rest of the cycle. For example, this is positive cycle. This is negative cycle. So from here, when Pt is negative, the power is absorbed by the source. So which means this is positive side. We are delivering. The generator is delivering the power to the resistor, inductor, or capacitor. But in the negative side, the resistive, the passive element deliver the power source back to the generator. So this is possible because of a storage element, like capacitor and inductor in a circuit. So the instantaneous average power change with the time and is therefore difficult to measure. So the average power is more convenient to measure. Usually we measure the average power. So the average power in watt is the average of the instantaneous power over one period. So we use mathematics again, 1 over t, from then I integrate it from 0 to t for the every instantaneous of the power. Then we found that this is the final equation. So since theta cos theta v minus theta I equals to cos theta I minus theta v, which is important is the difference in the phase of the voltage and the current. So we found that P equals to actually half Vm times Im cos theta v minus theta I. This is the final equation. You just need to remember this one. So we also can put in phasor form like this. And P equals to half real of a V times I of a conjugate. So we can put like this. Half Vm Im cos theta v minus theta I. So interestingly, if theta v and theta I is the same, which means the voltage and the current are in phase. This implies a purely resistive circuit. So we can use this equation to say that half Vm times Im, which is half Im squared times R, which is also equals to I squared over R. Okay? Yeah, when theta v minus theta I is equals to plus minus 90 degree, we have a purely reactive circuit, whereby half VMIM cos 90 degree become 0. Which means that if let's say the circuit only have a capacitor, or the circuit only have a inductor, purely inductor lah, then the power will be 0. Because they absorb and then they also deliver back to the generator. So the resistive load R, it absorbs power all the time, while a reactive load L or C absorbs 0 average power. So let's have a look on the example. Vt equals 120 cos 377t plus 40 and it. Now we want to find the instantaneous power and the average power. So instantaneous power P equals Vi, where we use this one times this one. So we have this one. Then we use this equation, then we can get this one, or in here. So the average power actually is half Vm times Im cos theta v minus theta I. Then we have a 344.2, which is this one. Okay? Another example. We can calculate the average power absorbed by an impedance. Z equals to 30 minus J40 when a voltage applied across it. So we want to find the average power, right? We need to know what is the equation. So P equals to half Vm Im cos theta v minus theta I. I have half. Do I have a Vm? Yes, 120. Do I have Im? No, I don't have Im. So what I need to do? I need to find it. So I equals to V over Jack. I have V, 120. I have Jack, like this. So this is my I. So come back to here. Do I have Im? Yes, 1.567. Cos, I copy. Theta V, where is it? Theta V is this one, 0. Theta I is 63. So 0, I copy 0. Theta I is 66.8. So I copy 66.8. Then I found that this is my average power, 37.24. Another sample, very simple equation, circuit. 5 angle of 30 degree, resistor 4 ohm, capacitor -2. So I want to find the average power absorbed by the source, and then the average power absorbed by the resistor. So first of all, I need to find the current first. I is actually this one divided by total load. So I found my I. And then the average power supplied by the voltage is actually, I use the equation half Vm Im cos theta v minus theta I. Where's my Vm? 5. Where's my Im? 1.118. Where's my theta v? 30 degree. Where's my theta I? 56.57. So this is my average power supplied by the voltage source. And then I also need to find the average power absorbed by the resistor. So very easy. P equals to half Vm Im, or what they use are Vm Im. Okay. So I need to find what is the Vm across the resistor. So V equals to 4 times I. So my I is 1.18 and 56.7. I get this one. So this is my I. So half Vm 4.472. Im 1.118. I have 2.5 watts. Effective or root mean square value, we call RMS value. Effective. The idea of an effective value arises from the need to measure the effectiveness of a voltage or current source in delivering power to a resistive load. So the effective value of a periodic current is a DC current that delivers the same average power to a resistor as a periodic current. Because our current is sinusoidal, we don't know which current we should take it. So usually we will use a RMS value to indicate the true value lah. So the average power absorbed by the resistor in the AC circuit is a P equals I think I think we directly talk about this one. How can we find the effective value of root mean square value? From the root mean square value, we already know that how to find it. Okay. First, although it is root, mean, and square, the first one is we must square it. Then we mean it. we find the average, then we root it because the value is a square, right? So which means if let's say I have an x value, many x value lah. First I need to square, I need to this equation I need to square all the every elements of the x value. For example, I have a x1, x2, x3. So x1 square plus x2 square plus x3 square, which is and then I need to average it. So average is usually I divide by 3, and then which is called mean lah. And then I need to square root it. So it is represent like this lah, actually represent in this form. And from those, maybe I go through lah. The average power absorbed by the resistor in the AC circuit. So P equals to, I want to find the average power of the resistor circuit from the V delivered to the resistor. Okay, so I need to find the effective RMS value. So it's a start from the average power absorbed lah. So and we know that it is a time domain, so it has time. So I need to find all the I square R over the time, and then I need to find the mean it. So I do some calculation. So I found that while the power absorbed by the resistor in the DC circuit is like this. DC circuit, which one DC circuit? DC circuit is like this. This is AC circuit, DC circuit. Then P equals to I effective square R. Then I equating the expression in 11.22 and 11.23. Solving for I effective, we obtain I effective equals to like this. And then the effective of the voltage also same in this way. So this indicates that the effective value is the root mean square of the periodic signal. Thus the effective value is often as the root mean square value or RMS value for the short. Which means because in the AC circuit it's a sinusoidal. So we don't know which point should we take. And usually we will use a value to indicate this is the rating. So in here we are comparing DC and AC. DC we have one effective value. AC we have instantaneous value. So from this equation we are try equating, saying that actually for the AC side we have a root mean square value, which is equivalent, same standard with the effective value. So we can write I RMS equals to I effective, or V RMS equals to V effective. And the general term is like this, whereby if let's say I have a few x value, I square the value first, and then I find the mean, and then I square root back. So this is called root mean square value. Root mean square. So VRMS. Okay, we can use this equation by using this equation with the assume that I equals to Im cos omega t. After derive, we found that I RMS value is actually equals to I peak divided by square root 2. Same as well, if let's say we start from Vt equals to Vm cos omega t, we can derive and found that V RMS equals to Vm over square root 2. If the I and V are pure sine wave. So find the average power in this one. We also can find the average power if let's say we have a Vm Im, right? We can change into like this form, and we found that Vm divided by square root 2 is a VRMS form. Im divided by square root 2 it is IRMS form. So in the average power in terms of RMS value, we can become P equals to VRMS times RMS times cos theta V minus theta I. Then we also write in this form, where P equals to I RMS square times R equals to V RMS square divided by R. So for example, we determine the RMS value of the current waveform in the figure 11.14. If the current is passing through a 2 ohm resistor, find the average power absorbed by the resistor. So we found that the time period is 4. So from this point going, and then it repeat again. See, so the period is 4 seconds. But every section it has a different waveform. So from 0 to 2 seconds, it is a 5t. This line is a 5t. From 2 to 4, it is a negative 10. And then again, 5t, negative 10. So we put into the equation. Then we do some mathematical calculation. We found that the RMS for this kind of the waveform, it is a 8.165 ampere. And then the power absorbed by the resistor value we use I square R. So RMS is 8.165 square times the R is 2. So it becomes 133.3. So this is the technique how we dissolve RMS value. Another example is a half wave. So we need to find a period first. So Vt actually is 0 to pi is 10 sin t, 10 sin t. Then another one is a 0. Then it will repeat. Okay. So I need to find the Vrms first. I apply this equation. Then I substitute 10 sin t inside, and then I do some calculation and changing with the trigonometry. I found that my Vrms is 5 volt. Then I want to find my average power dissipated in 10 ohm resistor, which is Vrms square divided by resistor. So I have 2.5 watt. So in order to find the Vrms, we need to find the Vt function. Where is the Vt function? Here. So apparent power and power factor. We saw that if the voltage and current at the terminal of a circuit are, Vt is a Vm cos omega t, It is Im cos omega t. So in the phasor form, Vm, we change to phasor form, V, Vm, cos, angle, theta V, Im, cos, angle, theta I copy. Then I apply the average power. P equals to half Vm, Im, cos theta V minus theta I. So we saw that Vm RMS, we also can convert this side to Vrms IRMS like this. So we know that Vrms times IRMS, actually it is we call as apparent power. So we can write S equals to Vrms times IRMS. And the rest power is product of the two items. The product is okay. Another one here, theta cos theta V minus theta I, we call it as a power factor. So the apparent power, it is in VA. P is in what? Apparent power is in VA. It's a product of the RMS value of average and current. RMS value of voltage and current. So this is my apparent power. S equals to Vrms times IRMS. And then I also can write like this. P equals to S times power factor. So power factor is a cos theta V minus theta I. Or I can write power factor equals to P divided by S, which is cos theta V minus theta I. So the angle theta V minus theta I is called the power factor angle. So let's have a look on the example. A series connected load draw a current IT like this. When the applied voltage Vt is like this. Find the apparent power and the power factor of the load. So apparent power is the S. Power factor is theta V, cos theta V minus theta I. Determine the element value that form the series connected load. So the apparent power S equals to Vrms times RMS. So Vrms is 120 divided by square root 2. 120, which is the Vm, divided by square root 2. 4 divided by square root 2. 4 is the Im, divided by square root 2, which is 240 in a VA. So the power factor is a cos theta V minus theta I. So my theta V is negative 20. My theta I is a plus 10. So it is 0.66. And then determine the element that form the series connected load. The power factor is leading. When it is leading, just for information, it is capacitor. Leading means the current leads the voltage. If we refer back to the capacitor that impedance for capacitance value, we'll see that the current is leading the voltage, and we know that it is capacitor. So the power factor may also be obtained from the load impedance, where Z equals to V over I. And I found my Z is V is equals to, I copy 120 cos angle negative 20, negative 20. And then divide my I. I is a 4, cos angle plus will be 10. So, I found like this. And then my power factor is cos negative 30 degree, this one, which is 0.66. And the low impedance X can be modeled by a 25.98 ohm resistor in series with a capacitor of this one. So XC is equal to negative 15. So how can we get this one? Actually, it's from here. Z equals to 25.98 minus J15. 25.98 actually is a resistor. Negative 15 is a capacitance value. So negative 15 equals to negative 1 over JC. 1 over omega C. So my C will be 1 over 15 omega. My omega here is 100 pi. So I found 212.2 microfarad. So determine the power factor of the entire circuit of a figure 11.1a. Okay, let's have a look on the simple circuit. We have the voltage source of a 30, angle 0 degree, 6 ohm, negative J2 ohm, 4 ohm. So first, what they want to do? They want to determine the power factor. Second, they want to know the average power delivered by the source. So usually we convert the circuit into simple circuit first. So we know that 6, this one is gonna negative J2 ohm is parallel with the 4 ohm. So we write in a 6 plus 4 parallel with negative J2. Then we do some computation. We found that the total impedance or equivalent impedance is 7 with an angle of negative 13.24 degree. Then my power factor is directly came from cos negative 13.24. So I found that it is 0.9734 in a leading form. Since the impedance capacitive is leading lah. Then the RMS value of the current actually now I want to find the average power delivered by the source. So what I do is I use a P equals to VRMS times RMS times power factor. So I need to find my VRMS. Where is my VRMS? Oh, VRMS is 30. Where is my IRMS? VRMS 30. Oh, okay. It stated that VRMS like this. So my VRMS is 30. Then my IRMS is 4.286. And then my power factor is 0.9734. Then I found that it's 125 watt. And then I need to find something. And then yeah, I also can find another way in this way. Okay, so thank you very much. Hope you enjoy it.